So we start with a pile of things, and on your turn, you can take as many things from the pile as you want. It has to be a non-zero amount, though. If you take things from the pile, you just get rid of them. And I put a box around this because when I was practicing, I said the opposite thing and forgot. Whoever can't make a move loses. So that means basically if there's nothing left, if you take the last thing, you win, equivalently. So what you can do in order to win here is just take away everything, and then you win. This game fucking sucks. Who would win this game? Well, I bet you're like, okay, Zev, why don't you talk about a cool game like chess? Well, that's not the type of game we're talking about. We're talking about a special type of game. These are called impartial finite games. Basically, impartial means it's like even for both players. There's no like in chess has different colored pieces, so that's not impartial. And chess is also only finite because the people who made chess went, oh shit, this isn't finite. We should put some weird rules in there to make it finite. So finite means the game will always end, and there's no sequence of moves that drags it on forever. And that's really important for me to do proof by induction properly, which I'm going to do a lot of. So that's a game. Well, I'm already like halfway through. It's like a minute. Let's play NIM more. Let's play NIM even more. But instead of one pile, let's play 2 games of NIM at the same time. So we're going to have 2 piles of things. 1, 2. And the way this game works is on your turn, you choose one of the piles, and then you make a move on that pile specifically. So, for instance, on my turn, I could do this. Now, why would I do this? Well, you definitely shouldn't do that. That's not a good move at all. But how do you know if it's a good move? How do I know that? This is really complicated. 6 and 4. What am I supposed to do? I don't know. Let's figure out how to win the game, which is the most important part besides having fun. No, if I wanted to have fun, I'd play chess. All right. How do you win these games? Well, you figure out what the winning and losing positions are. And basically some terminology. A winning position means if you have that position, you're going to win, as long as you don't mess it up. Don't mess it up. And losing position means if you have that position, you're going to lose, as long as your opponent messes it up. Everyone, please play these games in a mathematically sound way. Or don't. That makes my job easier if I'm trying to beat you. So, this position right here. I know there's nothing there. That was intentional. This position right here, it's empty, right? Let's say it's my turn, and this is what the board looks like. What am I supposed to do? There's nothing for me to take, so I lose. So that's an L right there. But what if I have a pile with a thing in it? Well, I can take the thing, and then I win. So that's a W. What if there's more things in the pile? Doesn't matter, because as we said at the beginning, I can take all the things, and I win, so I get the W, and my opponent will get the L. But what if I have what if I have 2 piles of things? Well, I don't know. This is too many things. So what if I just have my 2 piles, each have 1 thing in them, right? This is the simplest 2-pile position. So let me think. Let's say I'm playing this game, and I would like to win the game. What should I do? Well, I have 2 options. I could take a thing from this pile. Unfortunately, if I do that, my opponent is going to win by taking this thing. And if I take a thing from the other pile, I think you all know what's going to happen. My opponent's going to take this thing and win. So it appears that this position is an L for me. But, what? It does, yeah. So, let's say there's 2 piles and they're like this, the second most simple 2-pile position. I could go through all the possible moves I could do. Or I could just say, hey, look at this. If I take this thing right here, then I give my opponent the L, which means I get the W. So, it seems like there's a recursive way we define the L's and W's here. So, a position, this is obviously recursive, so we have to have a base case. If you can't make a move, it's an L, right? Because then you lose. Because the thing in the box says so. Is this too low? This is good, right? Or no, but the thing is here. What am I doing? I'll make it up more when I start moving over here, which I might do. can move to an L position, then you've got a W position, because you can give your opponent the L. So W's can move to L's. They might be able to move to W's also, but what's important is that they can move to L's, right? So if you can move to L to a losing position, you have a winning position. Otherwise, you have a losing position. Does that make sense? Okay, good. Because even if I can move to these W's, I simply won't do that. And instead, I'll move to the L. If I do that, then that's called messing up the game. It doesn't mean you're guaranteed to win, it just means you have a perfect winning strategy, which you can employ. Let's play a different game. This game, I'm kind of bored of it. What if I play the subtraction game? So I'm going to start with a number. Someone give me a number. 17. Someone said 7 and someone said 17, so I'm going to add those things together and make it 17. Yeah, that's right. So this game, it's like NIM, but it's you have 17, then you have a number, start with a number, and on your turn, you have 3 options. You either subtract 1, so you subtract 1, I can actually draw these. Good, yeah, that's right, look at that. 1, 2, or 3 things. So I can subtract 1, 2, or 3 things from my 17. And whoever can't make a move loses. Is this a winning position or a losing position? Well, I don't know. I do. But I don't know. What? How do I figure this out? Let's use induction, kind of. Yeah. What if my number is 0 and it's my turn? Well, that's an L. I'm going to lose. What if it's 1? Well, I can take 1 and make it 0. So that's a W. If it's 2, I can take 2. If it's 3, I can take 3. If it's 4, I can only take 1, 2, or 3. So no matter what I do, I give my opponent the W. So that's an L. Now, 5, 6, and 7 can all move to the 4. So they're all W's. But 8 can only move to 5, 6, and 7. So it's an L. There seems to be a pattern here where any position, if it's equivalent to 0 modulo 4, so if it's a multiple of 4, then it's an L. And I can prove this by induction. This is why it's important it's a finite game. Base case, if I have a position which is a multiple of 4, I can only move it to stuff that's not a multiple of 4, and by the inductive hypothesis, those are winning positions, so it's a losing position. And if it's not a multiple of 4, I can move it to a multiple of 4 by subtracting something, so by the inductive hypothesis, I can move it to a losing position, so it's a winning position. So good. Many games will have patterns like this, which you can exploit to bedazzle your opponents by starting with 1 billion and winning every time. As long as you make your opponent go first. Or if they don't know how to play and they make a wrong move, that could happen too. So, we know how to win games. So you could say that we're done being good at games. But do we just want to be good at games? I promised you that I would needlessly overcomplicate the games, and I intend to deliver on that promise. So, NIM. How do you win this 2 piles game of NIM? Well, I'm going to presume, I'm going to prove that you win, that if you have 2 piles of NIM, you're in a losing position, so that's an L, if and only if the piles are the same height. So let's prove it by induction really quickly. If they're both 0, base case, it's a losing position. Good, that checks out. Let's say they're the same. On my turn, I have to make them different, which means by the inductive hypothesis, I'm making it into a winning position. I'm going to stop saying by the inductive hypothesis. I think you can tell when I'm using it. Which means I'm making them a winning position, and which means I have a losing position here. But if they're different, I can take from the bigger one to make them the same. So I'm making it a losing position, so that's a winning position. Good times. Let's play NIM more, but let's actually do something else besides play NIM. Actually, we're not going to. I lied. I'm going to say forget NIM and imagine my favorite game, the abstract game. It's called the abstract game because I don't actually know any of the rules. I just know that it's a game, and it loosely fits my definition of what a game is. I'm going to call this position in this game G, because G is for game. And I'm going to define an equivalence relation, and I'm not really going to prove it's an equivalence relation till the end. You're going to have to trust me. saying that two games are equivalent. Oh shoot, I messed this up the same way. Okay, I'm going to define the notion of adding games together. So if I have two games, I can add G and H, I can add them together and play G plus H. And the way it works, it's the same as the two piles of Nick. On my turn, I choose G or H, and I make a move on G, or I make a move on H, using their respective rules. They could have the same rules, different rules, doesn't matter. I'm going to define an equivalence relation and say G is equivalent to H if and only if G plus H is a losing position. And just as a sanity check, I'm going to check that this equivalence relation is reflexive. So I'm going to check that G is equivalent. This might be too low. I'm going to check that a game is equivalent to itself, because if the game doesn't have any legal moves, then this is a losing position, right? So it fits the definition. If this game does have legal moves, then here's what I can do if I'm the second player, right? So my opponent has this position. I want to make sure my opponent will take that L. So let's say they make a move here and they move this to G prime, right? Since these are the same game, I can move to G prime. And then by induction, I've put them back into a losing position. Which means that this was a losing position, because no matter what they did, I would give them back a losing position. And they're going to lose. So the symmetry is obvious. The transitivity, I'll get to it. So this equivalence relation, and this works with the nim piles, right? Because only if the nim piles have the same number, then they are the same thing. There's another word that sounds like number. I'll get to it. So I'm going to define that now, actually. I lied to you. See how this says numbers? It's not numbers. Ooh. Cue the ooh. It's the nimbers. What is that? Why is he up here making up words, you are all thinking? Well, I didn't make up this word. It's a very real word. And it's called the nimber because I'm going to define it for you. I'm going to define it by saying that a position that has nothing you can do from it has a nimber of 0. And then I'm going to say a position's nimber, so the nimber of a position in a game like G, right, is the minimum excluded value of the nimbers of the things G can move to. I know it's a lot, but I'll give an example. So minimum excluded value, since we're doing combinatorics, the natural numbers are 0, 1, 2, 3, etc. So let's say G can move to something with a number of 0 and something with a number of 1. Then G's number is 2, because 2 is the minimum excluded value. And even if it can also move to something with 5, this is still 2, because that's the minimum excluded value, right? And if it can move to something with a number of 1 or 2, then it has 0 as its value, right? And the first thing I'm going to do with this whole notion of nimbers, this is what lets you combine games properly. And we're going to see how it's useful when we play a game with 3 piles. The first thing I'm going to do is say, G is a losing position if and only if the nimber is 0. And this hopefully should make sense. Let's say G is a number of 0, right? Well, for the base case, it's true, right? Induction. Let's say G is a number of 0. Then, by the definition of this minimum excluded value, I can only move it to stuff with non-zero nimbers. And by my induction, those are all winning positions. So that makes G a losing position. And contrarily, I can, conversely, yeah, there we go. If it's non-zero, then minimum excluded. In order for that non-zero number to be the minimum excluded value, I have to be able to move to 0, which means I can move to a losing position, which means it's a winning position. Let's say, oh man, what was I going to do next? We have nimbers, we have more nim. We're going to play more nim. We're going to figure out what's the nimber of this. Yeah, that's right, we're back at this. So I know already that to win this, I do that, right? If it's my turn, I want to do this, and then I win. But let's say I want to know the nimber, right? Well, what can I do? I'm going to claim, and this is you're going to hate me for this one, but binary exclusive OR operator, bitwise exclusive OR. That's what I do to these numbers. So this is 6, and this is 4, right? So in total, this 6 is, 1, 1, 0, and this 4 is 1, 0, 0. So basically, for those of you who are not in like CS or whatever, exclusive OR means if they are the same, you make it 0, and if they are different, you make them 1. So it's the same as adding in a ring with 2 elements, or a field with 2 elements for math people. So everyone should know what it means in one of those 2 ways. So this, the 2 zeros make a 0, the 0 and the 1 make a 1, and the 2 ones make a 0. Oh wow, we figured it out. Okay, so this, in total, has a number of 2. How is this helpful? Well, I know that numbers of 0 are my losing positions. So let's say, I like 2 things I want to prove. Okay, I'll do both of them real quick. Let's say I'm playing nim with 3 piles, right? Since this whole exclusive OR thing, I can apply it finitely many times. It doesn't have to just be 2 of them. Oh, I should probably prove that this exclusive OR thing, I just sort of said it. Okay. It's got this, we know this is 0, 1, 0, right? Okay, base case, it works with zeros. We know that. One of these positions has to have a 1 somewhere, right? To find out which one's bigger, right? It has to start with a 1, right? Since I can make this any lower value, I can change all of these bits in any way I want. And if I change these bits in any way I want, that's the same as changing these bits in any way I want. So I can, whatever this, I can like change this combined exclusive OR value to whatever I want. So in particular, I can make it 0 by changing this in some way. Does that make sense to everyone? That was not rigorous at all, but hopefully it makes sense. I take the bigger one, do something to it, make it the smaller one, and that makes them equal, right? And so, or actually in particular, I can make it any lower value than this, but I can't make it the same because I have to change one of these bits. That's why this is the minimum excluded value. So it's the number. And it works with 3 piles too. You can see here I have 3, 2, and 1. And this is 1, 1, 1, 0, 0, 1. So if I do that operation, it makes 0. Yeah, it makes 0. 1 minute. Now I'm going to prove a theorem. So remember this equivalence relation that I defined? Any game of this sort is equivalent to a single pile of nim. And this is a sort of famous theorem in combinatorial game theory called Sprague-Grundy theorem because 1 or 2 people whose names had Sprague and Grundy in them made this theorem. I don't know the people, but I'm sure they're nice fellows. What did I say? Oh yeah, it's long here. Okay. Yeah, that's equivalent to a pile of nim. Or more accurately, I'm going to prove that 2 games are equivalent if and only if they have the same number. And I guess I could use the binary exclusive OR thing to prove that. But I'm not going to use that. I'm going to use good old-fashioned proof by induction. So let's say I have 2 of them that are the same number. So I have G and H, and they both have the same number, N, right? Then, if I make a move, I have to make the number different, because it's the excluded value. I have to make it different. So whichever one I move on, we're going to make them have a different number, which means, by induction, that they will not be equivalent anymore. If they have different numbers, then I figure out which one is bigger, and I make that the smaller one. I make a move on it. So if m is greater than n, I make a move on m, which turns it into n, which is possible, because it's the minimum excluded value. So I can always move to a smaller number thing. And that makes them the same, so I can move to a losing position. So it's a winning position, so these are not equivalent. And I still got time left. Okay. And so that's, so that's the sort of thing that's happening here, is this is a losing position, but if I have like this, right? I see that this has 4, right? And these together have 3, so I can turn this 4 into a 3, right? That's just an example, but you can use any games you want. You know what? I'm just gonna be like, all right, Any questions? Okay, thanks. Mary has a question.
You should challenge someone to a multiple at a couple rows and see if they've learned it.
Ooh, Mary, come up here. All right. We're gonna play. Do you want to play NIM or do you want me to like make up a game on the spot? We're gonna play that.
Well, I feel I don't know.
All right, we're gonna play NIM. I'm gonna just like do.
You're gonna draw some circles, no counting aloud. Or we just don't show each other how many you draw.
Yeah, exactly. Okay. Except these games I drew over here, they have different rules. These three piles. It's a different rule.
Oh.
So from these three piles, you can only take one thing at a time if you move on one of these piles. You only let us take one thing. Yeah, that's right. But these are regular NIM. So you can take as much as you want if you choose one of those piles. So, all right. You want to go first, or do you want me to go first?
May I have at least a second to like consider?
Oh yeah. Well, let's both take a second and consider. Thank you for helping me.
As opposed to just like, I should just go. Okay.
Oh, wow. Look at you. All right, I'll go next. Mary knows what she's doing. She's winning. Look what's happening to me. All right, I'm going to take one from you now. Yeah. All right. I know this is intense.